Okay, so you sent us a ton of material on probability, inference, and machine learning. Wow. This is going to be a deep dive.
This listener's ready to go deep.
But don't worry, we're up for the challenge. Let's try to extract some of those golden nuggets of knowledge for you.
Yeah.
It looks like you've been digging into research papers on this topic. What's really fascinating to me is how all these concepts connect, like how they help us understand the world, and even build those like powerful machine learning algorithms we hear so much about these days.
Yeah, it's quite a journey, starting with probability, the foundation of it all. Your source material dives right in talking about probability spaces. It might seem a bit abstract at first, but it's actually quite intuitive.
Okay, so let's break that down a bit. What is a probability space and why should we care?
Well, think of it like setting the stage for talking about probability. We need to define what possible outcomes we're considering. That's our sample space. Then we need a way to talk about events, which are collections of those outcomes. That's where the sigma algebra comes in. And finally, we need a way to assign probabilities to those events, which is done with a probability measure.
So the probability space is like the blueprint for our probability calculations. It defines the playground, the rules of the game.
Exactly. Now, there's a term that popped up in your material that I found interesting, the Borel sigma algebra. Have you ever wondered how we can apply probabilities to things like temperature or stock prices, which can take on any value within a range?
Now that you mention it, yeah. That always kind of puzzled me. How do we deal with those continuous values?
That's where the Borel sigma algebra comes in. It's like a special toolbox that lets us measure all those reasonable subsets of real numbers, ensuring that our probabilistic models can handle the messy, continuous data we find in reality.
So when you see a stock price above a certain threshold, you can thank the Borel sigma algebra for allowing us to calculate that probability.
Exactly.
Wow. Okay, that's actually pretty cool. I never thought about it that way. It's like the Borel sigma algebra is the bridge between the abstract world of math and the concrete world of measurements.
Exactly. And speaking of things that can vary, your source material delves into probability distributions, which I think you'll find fascinating.
Okay, probability distributions.
Yeah.
They ring a bell. Remind me what they're all about.
They're all about understanding how likely different values of a random variable are. Think about rolling a die. Each face has a 16 chance of coming up. That's a probability distribution. Now, for continuous variables, like temperature, we use probability density functions, or PDFs, which tell us the probability of the variable falling within a certain range.
Right. Now I remember. So we have these distributions, these PDFs, that describe the likelihood of different events. But how do we actually use them to solve problems?
That's where the law of total probability comes into play. And this is highlighted in the research paper you sent us. Sometimes calculating a probability directly is like trying to solve a complex puzzle. The law of total probability says, hey, let's break this down into smaller, easier to manage pieces.
So it's a divide and conquer strategy for probability. I like it.
Exactly. And the key is to condition on another event that simplifies things. For example, let's say you're wondering about the probability of your favorite team winning the championship. You could use the law of total probability and condition on whether they make the playoffs. So you would calculate the probability of them winning given that they make the playoffs, and the probability of them winning given that they don't make the playoffs.
That's a much clearer example than getting stuck in traffic. So we break down a complex probability into smaller conditional probabilities that are easier to calculate, and then combine them to get the overall probability.
Precisely. Now, your material also delves into the concept of independence between random variables. Imagine flipping a coin twice. The outcome of the first flip doesn't affect the second.
Yeah, that makes sense. Each flip is a fresh start.
That's independence in action. And your research paper defines this concept using the conditional cumulative distribution function, or CDF, basically stating that knowing the value of one independent variable doesn't give us any information about the other.
So it's like knowing you flipped heads on the first toss, it doesn't change the 50-50 odds for the next one.
That's a great way to put it. So independence means one event doesn't snitch on the other. They keep their probabilities to themselves.
Exactly.
And speaking of intriguing concepts, there's this tower rule mentioned in your research. It might sound a bit daunting, but it's a clever tool for calculating expected values. Basically, it says we can break down the overall expected value into smaller, conditional expected values, making calculations much easier.
So it's like the law of total probability, but for expected values.
You got it. It's all about finding clever ways to simplify calculations. And finally, your research paper introduces covariance, and variance, which are essential for understanding how random variables relate to each other and how spread out their values are. Covariance measures how much two variables move together, like ice cream sales and temperature. If they both tend to increase or decrease together, their covariance is positive. Variance, on the other hand, measures how much a single variable deviates from its average. Think of it as a measure of how wild or predictable a variable is.
Okay, so we've got these tools for describing probability, these distributions, laws, and measures of spread. But where does inference come in? How do we actually use all of this to make sense of the world?
That's a great question, and I think you'll find this next part particularly fascinating. Inference is like being a detective, but instead of a magnifying glass, we use probability as our tool. It's about using what we know to draw conclusions from observations, even when we don't have all the pieces of the puzzle.
So it's like probability in action. We're not just describing events, we're using probability to figure things out.
Exactly. Now, your source material makes a distinction between logical inference and plausible inference. Logical inference deals with absolute certainty. Like, if we know all cats have tails and Whiskers is a cat, then we can definitively say Whiskers has a tail. No doubt about it.
Okay, that seems pretty straightforward.
It is. But in the real world, we often deal with uncertainty. That's where plausible inference comes in. It allows us to draw conclusions even when things aren't so black and white.
So give me an example.
Imagine you see wet pavement outside. Can you logically infer that it rained?
Not necessarily. Maybe a sprinkler went off or someone was washing their car?
Exactly. Plausible inference takes those possibilities into account. It considers things like how often it rains in your area, whether it's sprinkler season, and other relevant factors to come up with the most likely explanation.
So plausible inference is like a more nuanced way of reasoning, where we use probability to weigh different possibilities and make the best guess based on the evidence and our prior knowledge.
You nailed it. And what's really fascinating is that your research points out that logical inference can actually be seen as a special case of probabilistic inference. It's like saying, I'm 100% sure it rained, is the same as saying the probability of rain is 1 up once.
Whoa, that's mind-blowing. It's like those two types of reasoning, which seem so different, are actually connected by this underlying language of probability.
Exactly. And speaking of connections, I'm curious about this concept of entropy you highlighted in your material. It comes up in the context of inference, and I'm wondering how it all ties together.
Honestly, entropy always seemed a bit mysterious to me, like something out of a physics textbook. How does it relate to all of this?
It's a really cool concept. Entropy is basically a measure of uncertainty. The more entropy, the less certain we are about something. Think of a coin toss. A fair coin has maximum entropy because the outcome is truly unpredictable. But if the coin were weighted to always land on heads, there's no surprise and the entropy would be 0.
So entropy is like a gauge for how much surprise an event holds. I like that.
Exactly. And your research delves into this maximum entropy principle, which basically says when we're choosing our beliefs, we should lean towards the option with the most entropy, especially when we don't have a lot of prior knowledge. It's like saying, don't assume things you don't know for sure.
That's a great reminder to stay open-minded and embrace uncertainty.
Absolutely. Now, your material also mentions Gaussian distributions. They're like the superheroes of probability and inference popping up everywhere because they have some incredibly useful properties.
Okay, I'm intrigued. Tell me more about these Gaussian superpowers.
For one, they have this remarkable stability. No matter how you slice and dice them, they remain Gaussian. This is crucial because it makes working with them computationally tractable. Imagine trying to solve complex equations if the distributions kept changing shape, a nightmare.
These Gaussians are like the reliable workhorses of probability. They're always there for you, no matter how complex the problem gets.
Precisely. And your source material dives into a really neat theorem about conditional distributions of jointly Gaussian random variables. Essentially, it gives us a closed-form solution for figuring out the distribution of one variable given the values of others, which simplifies things immensely.
That sounds like a really handy tool to have in your probability toolbox.
It is. And speaking of tools, I think we're ready to move from the world of static probabilities to the dynamic world of change, which is where your material starts exploring stochastic processes.
Okay, stochastic processes. I've heard that term before,
Oh,
but it always seemed a bit intimidating. What are they and why should we care about them?
they're basically sequences of random variables that change over time. Think about tracking the stock market or weather patterns. Those are stochastic processes in action.
So instead of just looking at a single random variable, we're looking at a whole movie of them, a whole timeline of how they evolve.
Exactly. And a really important type of stochastic process mentioned in your research is the Markov chain. Imagine a frog hopping between lily pads. Each lily pad represents a different state, and the frog's hops are transitions between those states.
Okay, I can see that frog hopping around.
The key idea here is that where the frog hops next only depends on its current lily pad, not where it was before. It's like having a short memory, only the present matters.
So it's like each hop is a fresh start, independent of the frog's past hops.
Exactly, that's the Markov property. And it simplifies things a lot because we don't need to keep track of the frog's entire hopping history.
Yeah.
Now you've highlighted these things called transition probabilities in your research.
Right? Those seem important. What are they all about?
They tell us the likelihood of the frog hopping from one lily pad to another. It's like a map that guides the frog's movements with probabilities assigned to each possible hop.
So we've got these states, the transitions between them and probabilities governing those transitions. What else do we need to know about Markov chains?
Well, we need to understand how they behave in the long run. Your research mentions stationary distributions, which describe the long-term probabilities of the frog being on each lily pad.
So even though the frog is hopping around randomly, there's a kind of predictability in the long run.
Exactly. And understanding these stationary distributions is super useful in lots of applications, like predicting customer behavior or understanding the spread of diseases.
That's fascinating. So we can use Markov chains to model all sorts of dynamic systems and make predictions about their long-term behavior. But what about making decisions? How do we actually use these models to guide our actions?
That's where Markov decision processes, or MDPs, come into play. They take Markov chains to the next level.
MDPs. Sounds intriguing. How are they different from regular Markov chains?
Think of it this way. With Markov chains, we're just observing the frog hopping around. But with MDPs, we can actually influence its hops by giving it rewards or penalties.
Like giving it a tasty fly if it hops to a certain lily pad, or a little splash of water if it hops to one we don't like.
Exactly. Those rewards influence the frog's decision-making. Our goal is to find a strategy or policy that maximizes the total reward the frog gets over time.
So we're not just modeling the frog's behavior, we're trying to teach it to be a smart hopper, maximizing its fly intake.
You got it. And to find that optimal policy, we can use powerful techniques like dynamic programming.
Dynamic programming.
Yeah.
Now that rings a bell, but I could use a refresher.
It's a clever way of breaking down a complex problem into smaller, overlapping subproblems. So instead of trying to find the best sequence of hops all at once, we solve it step by step, building upon the solutions we've already found.
So it's like figuring out the best way to hop from each lily pad to its neighbors, and then using that information to find the overall best path.
Exactly, and algorithms like value iteration and policy iteration, which are mentioned in your material, use dynamic programming to find those optimal policies.
Okay, so now our frog is a strategic hopper, navigating the lily pads like a pro. But what if we don't know all the transition probabilities beforehand? What if the frog's world is a bit more unpredictable?
That's a great question, and it leads us to the exciting world of reinforcement learning.
Reinforcement learning. It's a term I've heard a lot lately, but I'm still not quite sure what it means.
Think of it as learning by trial and error. We let the frog hop around, observe its rewards, and gradually update our estimates of the transition probabilities based on its experiences.
So we're learning on the fly, adjusting our strategy as we go, kind of like how we learn in the real world.
Exactly. And within reinforcement learning, there are different approaches like model-based and model-free methods.
Can you explain the difference?
Yeah.
I'm curious to know how they approach learning.
Model-based methods try to build an explicit model of the environment, like creating a map of the lily pads and their connections. Then we use that model to plan our actions.
It's like being a cartographer, mapping out the territory before we explore it.
In a way, yes. Model-free methods, on the other hand, don't bother building a model. They just learn directly from experience by associating actions with rewards.
So it's more like, let's just jump in and see what happens.
Exactly. And there are pros and cons to both approaches. Model-based methods can be more efficient if we have a good model, but they can be brittle if the model is inaccurate. Model-free methods are more robust to model errors, but they can be slower to learn.
It sounds like the best approach depends on the situation. If we have a reliable map, model-based makes sense. But if things are constantly changing, model-free might be a better bet.
You've got it. There's no one-size-fits-all solution in reinforcement learning. It's all about choosing the right tool for the job.
This is fascinating. It's like we're starting to unlock the secrets of how machines can learn to make decisions in complex dynamic environments. But what about those situations where we don't even know the current state? What if we can only see a blurry shadow of the frog, not which lily pad it's actually on?
That's where we enter the realm of partially observable Markov decision processes, or POMDPs, which are even more challenging.
POMDPs. It sounds like a mouthful.
Yeah.
But the idea of not knowing the exact state is really intriguing. How do we deal with that extra layer of uncertainty?
With POMDPs, we have to deal with uncertainty not only in the future, but also in the present. We have to infer the frog's current state based on our observations and then plan our actions accordingly.
So it's like detective work and strategic planning all rolled into one.
Exactly. And POMDPs are incredibly powerful because they allow us to model a wide range of real-world problems from robot navigation to medical diagnosis.
Wow. It's amazing how far we've come from those basic probability concepts. We've explored inference, Markov chains, MDPs, and even POMDPs. It's like we've built this incredible framework for understanding and making decisions under uncertainty.
It's a truly remarkable framework that underlies much of what we call artificial intelligence today.
And it all goes back to probability. As we've been talking about all this, something that's been on my mind is, as we've been talking about all of this, something that's been on my mind is how all of this connects to human intelligence. We talked earlier about our brains potentially doing Bayesian calculations, but I'm wondering if there's an even deeper connection between probability and how we perceive the world.
Yeah, that's a fascinating question, and one that researchers are still exploring. Some theories suggest that our brains might be using probabilistic models to make sense of sensory information, predict future events, and even understand other people's minds. After all, we're constantly bombarded with incomplete information, and yet we manage to navigate the world remarkably well.
So you're saying that our perception of reality might be inherently probabilistic. We're not just seeing the world as it is, we're constantly making probabilistic judgments about what we're seeing, hearing, and feeling.
Exactly. And that makes sense when you think about it. Our senses aren't perfect. There's always noise and uncertainty. So our brains have to fill in the gaps, make educated guesses, and constantly update our beliefs based on new evidence. It's like we're running these complex probabilistic simulations all the time without even realizing it.
That's mind-blowing. It makes you wonder what other probabilistic tricks our brains might be up to. But let's bring it back to the material you sent us. We've covered a lot of ground from basic probability to these sophisticated decision-making models. But I'm curious about the practical side of things. In the real world, data is often messy and unpredictable. How do we deal with that when we're trying to build models and make inferences?
Right. That's where we start delving into the nitty-gritty of dealing with real-world data, which is rarely as clean and perfect as we'd like. Your material actually touches upon this when it discusses parameter estimation. It's all about figuring out the best values for the parameters of a model, like the mean and variance of a Gaussian distribution, to make it match the real world as closely as possible.
So it's like fine-tuning the knobs of our model to get the clearest signal, the most accurate representation of the data. But I'm guessing it gets tricky when we have noise and errors mixed in.
You bet. And the source you shared emphasizes the importance of understanding how those errors are distributed. Are they Gaussian? Are they outliers? The characteristics of the noise can really throw a wrench in our estimations if we're not careful.
So it's not just about finding the average. It's about understanding the texture of the noise around that average.
Yeah.
We need to know if it's a gentle hum or a cacophony of static.
Exactly. And that brings us to another important topic highlighted in your material, optimization. It's essentially about finding the best solution to a problem given certain constraints. In the context of parameter estimation, we want to find the parameter values that minimize the errors or maximize the likelihood of the data we observe.
So we're trying to find the sweet spot, the perfect configuration for our model that balances accuracy with simplicity.
You nailed it. And there's a whole zoo of optimization algorithms out there, each with its strengths and weaknesses. Gradient descent is a popular one, but there are many others to choose from depending on the problem at hand.
This is all starting to click now. We start with probability, use inference to draw conclusions, estimate parameters based on data, and then use optimization to fine-tune our models. It's like a powerful toolkit for making sense of a messy and uncertain world.
It is, and remember, these concepts we've been discussing are the very foundation of many machine learning algorithms. Those algorithms that can predict your next purchase, translate languages, or even diagnose diseases, they're all built upon this bedrock of probability, inference, and optimization.
It's amazing how much we've covered in this deep dive. You've given me so much to think about, and I feel like I've gained a whole new appreciation for the power and beauty of probability. It's not just some abstract mathematical concept. It's woven into the fabric of how we understand the world, make decisions, and even how our brains might work.
It's been a true pleasure exploring these ideas with you. And remember, the world of probability, inference, and learning is vast and ever-evolving. There's always more to discover, more connections to make, and more questions to ask.
Absolutely. Thanks for being such a fantastic guide on this intellectual adventure. I'm sure I'll be back with more questions and more fascinating materials to dive into. Until next time.